Welcome. In this video, I'll be going slightly rogue and covering a topic that, as far as I can tell, is not covered in any standard course in the whole Danish school system. Namely, the topic of sub-factorials. A sub-factorial is the number of derangements of a sequence. That sounds super fancy, but it's not that fancy. What it means is, let's say we have a matching test, okay? So we have a bunch of questions and the same number of answers, and we just want to match the answers to the questions, right? If we do this correctly, we get full points. If we put all the answers correctly to all the questions, we get full points. A derangement is simply an arrangement of the answers that gives 0 points, such that we've moved all the correct answers out of order. That's what it is. The notation for the sub-factorial, as the name might suggest, is this inverted exclamation mark, the Spanish exclamation mark. Another notation for that is also just using the standard exclamation mark but putting it in front. Personally, I feel like that might give some confusions, so I'm going to use the inverted one because it's completely unique compared to the other one. It's also slightly symmetric, so I like that. Alright, what I'm going to be proving are 3 formulas for to calculate the sub-factorial. 2 iterative formulas and 1 closed form formula, as you can see here. The first formula is calculated by using all the previous sub-factorials, so you need to do a lot of calculations. The second, the green one, only uses the 2 previous sub-factorials to calculate the next one. And the red formula is simply a closed form, so you just need the length of the sequence, boom, and you're done. Beautiful. All right, well, let's just get going because I'm not sure I have that much time. All right, so let's say we have, just like before, we have a correct order of the answers, and let's use a super boring name, A, B, C, D, E. So that's the correct order of the answers, all right? And now I want to move them out of order. How can I do that? Well, I can start by moving the A out of order. And how many ways can I move the A out of order? Well, I can move the A out of order in this many ways. So if the string has length n plus 1, or the sequence is length n plus 1, that can be done in n ways. And they're all symmetric. They're completely symmetric. If I put it in B, it's pretty much the same as putting it in C. All the arguments that follow will be completely analogous. All right? Okay, so let's say, we can say without loss of generality, that we put it in B's place. So what we end up with is something like this. So we put A in B's place. Now we have to place B, but now we're completely free to place B wherever we want. We already ruined B. B can't be right. And our whole goal here is to be wrong, to get 0 points. Alright, so there are 2 cases. The first case here is I put B where A used to be. Alright? But now I'm in the similar situation. I have BA, and then I want to jumble the rest of them. I want to find the derangements for the rest of the sequence. But that's exactly n minus 1 sub-factorial. That's the first case. The second case, is, okay, B does not go where A was, but it goes in one of the other places. Again, this is totally symmetric. So I'll just say, sure, I'll just put it in C's place. So now it looks like this. Alright? And I could have done this in n minus 1 ways. I could have done this in n minus 1 ways. But I chose C because they're all completely symmetrical. Alright? Now I have to place C. Again, now I'm totally free to place C anywhere because I've already ruined C. I've already answered C wrong. I can put it here or I can put it here. But this is the exact same situation I had with B earlier. So I can follow the exact same argument and I get n minus 2 sub-factorial n n minus 2, and so forth. What I end up with here is this pretty nice formula that says that the n plus 1 subfactorial is equal to, well, I had n here, and then I have to multiply by the two cases that were in there, which was n minus 1 subfactorial plus n minus 1, open parentheses. And what goes into the parentheses? Well, the exact same thing. I go n minus 2 subfactorial plus n minus 2. And this continues. And this continues all the way down to 3 subfactorial plus 3, 2 subfactorial plus 2, 1 subfactorial plus 1, and 0 subfactorial plus 0. And I gotta close a bunch of parentheses because these are nested parentheses. Right. If I multiply this out, I multiply this n on this and this, I end up with n times n minus 1 subfactorial. That's this first thing. Then I get n times n minus 1, this times this, times this. And then I keep going. I keep going. And at the very end, I have 3 subfactorial multiplied by this times this times this times everything. And what I end up with is divided by 3 factorial. Oh shoot, my bad. What I meant was n factorial divided by 3 factorial, 3 subfactorial. You can see that by this pattern. You can pause it if it's not obvious. And then I get n factorial over 2 factorial 2 plus n, boom. N factorial, 0 factorial, 0 subfactorial. And as I've tried to indicate at the bottom here, what I really have here is I have this really nice formula. I have the sum of n factorial over k factorial, k subfactorial, where k goes from 0 to n minus 1. But this is exactly, I can just, n factorial is just a common factor in all these terms, so I can move it outside this sum, and when I end up with this k subfactorial divided by k factorial, k equals 0 to n minus 1. Isn't that beautiful? So wonderfully symmetric. That wasn't that bad. The maybe the worst part is just wrapping your head around that this is actually the same as this. Or sorry, this is the same as this, but once you put your head to it, it's not that bad. All right. Now I want to continue with the green one. This is pretty problematic to calculate because you need all the. Let's say we're doing this for 100, then you need to do 99 calculations. Hell no. I want to do 2 calculations. That's it. All right. So let's continue here. Okay. So I take this thing here and I extract the highest term. I take this highest term out. Maybe this could be done more nicely, but this is how I'm doing it. Okay? So I take this highest term here out. So I have n factorial times n minus 1 subfactorial divided by n minus 1 factorial. So I've extracted this highest term here. Then I multiply this onto the rest of the sum. And what I have left then is I have from k equals 0 and then I take this leading n outside the factorial. And what I have here, this is exactly the definition of n subfactorial by the formula we just showed. So this is simply, and the n factorial, just like here, this n minus 1 factorial cancelled with the denominator here. So I have n minus 1 sub-factorial plus n times n sub-factorial. We have a common factor of n. We can put outside the parentheses. So we have n sub-factorial plus n minus 1 sub-factorial. Isn't that beautiful? So it's pretty easy to calculate, iteratively at the very least. But iteration is not always the most convenient. Personally, I always like if I can get a nice closed form, okay? But the closed form actually follows pretty nicely from these two results. So we'll get to that now. Wonderful. And if you need a moment, you can just scroll back and pause. Now we get to the red part, all right? So what I'm going to do is I'm going to do a proof by induction. So I'm going to assume it's true for all the lower indices or lower values. And then I'm going to show that it's also true for the next one, right? And since I know this is true trivially for n equals to 0, 1, and 2, we have a really nice base that we can build off of, all right? And then I simply put n plus 1 into that nice little formula, like always, on the right side. So I put the right side, I write up the right side, and then at the very end I'll show that it's the same as the sub-factorial. Okay, so I have n plus 1, factorial, the sum to n plus 1, k equals 0 of k sub-factorial over, oh shoot, this is the new formula, minus 1 to the k factorial. So no sub-factorials, now no iteration at this point. Okay, I do something extremely similar. I extract the highest term. Okay, I extract the highest term. Okay, so I get n plus 1 factorial, and then it goes minus 1 to the power of n plus 1 divided by n plus 1 factorial. That's the highest term, all right? And then I have everything else. Oh, maybe I can fit it here. N plus 1 factorial, and then the sum again, but now it only goes to n. Alright? But this little beauty here is exactly n sub-factorial times this leading factor here, right? Just so I have more room, I'm going to move it all the way over here, and this cancels with this. So I have minus 1 to the power of n plus 1, and then plus n plus 1 times, oh shoot, n sub-factorial. Okay, I can expand this, so it's minus 1 to the n plus 1. Yeah, actually, let's just, I don't want to drag this minus 1 to this power along. Let's just start with this, okay? So, let's just, for a second, let's forget this and just focus on this. So this is equal to n times n sub-factorial plus n sub-factorial. Okay, now I want to use this green formula. Okay, I want to use this green formula, which means that what I get here is I get n sub-factorial, not on the first one, but on the second one. So I get n minus 1 times n minus 1 sub-factorial plus n minus 2 sub-factorial. This can probably be done way more elegantly. This is what I have right now. Sorry. Again, I expand the parentheses, and I get n times n minus 1 subfactorial minus n minus 1 subfactorial plus n minus 1 n minus 2 subfactorial. Oh, that fits so nicely. Wonderful. All right. If I look at this, what I have here is I have n common factor in these two things, n subfactorial plus n, n minus 1 subfactorial. Well, we just showed that this is the same as the n plus 1 subfactorial. Amazing. So we can already tell we're getting somewhere. All right. Minus this. So this is minus, and then this is n minus 1 factorial sum to n minus 1 k equals 0 and minus 1 to the k factorial. This is from this term here, and then I have plus n minus 1 n minus 2 factorial, the sum n minus 2 k equals 0 minus 1 to the k over k factorial. All right. The beautiful thing here is that this becomes n plus 1 subfactorial. This n minus 1 factorial is the same as this, because I can just multiply this and then I have n minus 1. So you have the same leading factor. And this sum is completely identical to this sum. These two sums are completely identical, except that this sum has one extra term. But all the other terms cancel because these have two different signs. The only term that survives this thing here is minus the top term. So we have n minus 1 factorial. Oh shoot. I think it's fine. Minus 1 to the power of n minus 1 over n minus 1 factorial. These cancel, and what I'm left with is this is a weird minus sign here. But what I had earlier is I had a minus 1 to the power of n plus 1, and then I have a minus 1 to the power of n minus 1. But every other power of minus 1 will have this. Will have the same sign. So if this is a plus 1, then this is also a plus 1. If this is a minus 1, this is also a minus 1. Which means that when we subtract these two, they cancel with each other. So this whole thing cancels with this thing, and what we're left with is this beauty here. Alright? Isn't that wonderful? Again, this is probably way more complicated than it was necessary, but this is whatever I came up with. Yes. So not much time, but another beautiful consequence of this closed form is this is actually the partial sums for the Maclaurin series for the exponential function to the power minus 1. Which means that you can actually calculate the n subfactorial as when you round n factorial over e. Isn't that crazy? It's absolutely gorgeous. Anyway, so the whole goal of this was to actually figure out the expectation value. What is the expected score in this matching test that I started with the presentation with? But I don't have time for that. That's going to be a totally different video. So in reality, this whole video was just a presentation of the Sub-Factorial and some nice formulas for it. Questions, comments, put them down below. I'll see you next time.